是不是？还是我现在再把这个 LLESport 这个台词，这个我们这个。
现在 NRG 胜率就1%，
你以为播入围赛的时候，你还觉得就可能入围赛会发生这样的事情？没有，进到了正赛，这类事情还在发生。突然一波日本身盲环到3个人，就算没晕住，但等离子飞弹就差一点要把 Contract 给烧死。但这波幸好是 Planet Fox 帮挡了虚空探索，但这 Contract 才被吓出了闪现，打野必须得回家。NRG 没有办法来防守这一条的巴龙 ，WBG 突然一波惊悚的开团。
好了，
吓得 NRG 满身大汗
，0.1%，
越来越低了
，0.1%。对，就感觉还是嘉文顺序高吗？
哎呀，那 Fnatic， 那现在看唯一能够去依靠的人，就好像又跟那个上一把 NRG 一样，又要靠杰西。但这不一样的是，除了靠杰西之外，另外一边伊泽也在叠魔剑，也在叠他的水滴。
250、240哦，感觉叠满都差不多可以上票嘞
，25分差不多。那再抬一下没抬到，尤其他们现在摸不了兵，要打 poke 也打不到的是 LNG 的人，叠不了水滴。已经连续空了2发 Q Humanoid， 这把犯下了致命失误之后，现在有我们机会来将功赎罪。突然是 Trimby 的一波开团，那 Gala 还是反应过来开出大绝，紧接着是 Scout 推出的一个绝望的控杀防壁，让对方的进场是化为了一朵泡影。LNG 只死了一个他斩就化解掉了这波的攻势，而且还反杀了对面2个人。不过在后续的追击当中 ，Noah 也击杀掉了 Zika。Rezo 还想要再去留住对方3个人的残血，但是 Rezo 的伤害真的不够。不过这一台有抬到了航，再往后交闪，他是成功的交换到了人头，自己还能够成功撤场。Noah 只能靠你了，这把还没有你的镜头要来做追击。Gala 没有闪现，没有大绝，在吸烟区里面有机会吗 ？Noah 再 Q 了一下，但是人已经走了。
这么胆小干嘛？对面双膝都没血没大，他为什么那么怕呀？他有闪的，
但可惜。
这波
没有把握住。
这波我觉得那个打野玩的蛮好的，他这波侧边的抬的很关键。
这波墙壁也是有稍微限制到 LNG 的一个走位。
这波抬到那个2个人很关键，我只能说。但是打完大概从0.5%，现在大概2%吧，3%胜率。
哎呦，那其实提升不少。
3%跟0.5%有区别吗？
其实这你用这个倍率来看嘛，现在涨了这个4倍4-5倍，
好吧。
对不对？4倍、5倍、6倍的，对不对？这样子涨看起来好像，其实胜率好像提升不少哦。
确实啊，但是好像还是很可悲，
还是很低。
3%，
这还是那句话嘛，不趋近于0，表示它有可能发生。
确实，
现在是一个盲视野的情况下，要回踩巴龙，但巴龙已经被 LNG 给拿下。这是航的一波反抬，但是反而自己被翻了回去，由 Rezo 拿到了 Killing Spree， 一个040的塔利亚，目前连拿3颗人头。
对，好像这个瑞空不太会打塔利亚。不过塔利亚确实真的很抗瑞空。前阵子啊，我自己只要看到瑞空，我就选塔利亚，
不太好受。
就那个地板一铺，瑞空就直接那个跟断了翅膀的鸟一样。
哎呦，我形容的特别好啊，就确实这个让你没办法去发挥你的机动性的这个扑眼，
是，这个没什么力的，输太多了。
哎呦，但是下面 LNG 双 C 其实有点踩不回来，但塔斩突然一波闪现 EQ 空了，而且还被对方的扑眼给晕住。不过盖了大绝之后有闪现，航的这波进场也控制住了对方的成员。不过惊人结束了，塔斩也是被对方给收了下来。Trimby 这是撑不住对方前排的伤害，突然一波闪现晕住 Oscar Ring。差1丝的血量就要被 Zika 给换掉，但是后续的追击 ，Noah 刚好被球果给弹回了 LNG 的脸上。那还有一个奥数月前来到了墙壁的另外一端 ，Scout 这是杀影把的再插过来，
这是温刀
无限的出征，这是对方的加重，这是对方的蓝区，这一波起跳在倒钩的收毛，拿下了对方的 Rezo， 仅仅只剩 Noah 一个人在苟活。
跳过去有机会啊，没机会，这个太肥了。
这是 Scout 撞到他的脸上，用护杀顺身收下了这个击杀，Humanoid 在这波不知道什么时候逃掉了，而且看起来是有把中路的塔给拔掉。
刚刚那个球果谁点的？不等多等一下嘛。
哎呀，看起来是Fnatic 球果赞，但也确实因为少了这个奥数月前，或许少了一点操作的可能性，但
这波
结果是一样的。
这波开得好，这个才是嘉文嘛，直接闪现开，很果断哦，就死了就算了，队友会搞定，把对面的 C 位拖住就行了。
没错 ，Humanoid 这波也是没什么办法，就打了一炮，发现伤害不太够，反而是 Scout 滑到他脸上，他必须下的交闪。鳄鱼、啊，
他好像也没办法不怪他那个沙皇的沙兵飞过来他不 A 他就被捅死啊！你死道友不死贫道嘛？
是，但结果论来说，他弹过去他还是死了，突然他多打了一个 AD 的E出来。
人的求生意志在当下是没办法的，
他只能看自己，
他不能抗拒他的本能啊！
哎呀，他是这个应激反应出现了，这个鳄鱼他要活，
是
他当下是眼中看不到他的队友的。
对啊，那个跟他又没什么关系。
哎，确实啊，这个死到临头了，就没什么办法了。
对啊。
怎么能活怎么玩吧，但他玩下来，最后是一个都没活。
他要是舍得牺牲自己去救他，那我要反而怀疑他们两个有点问题。
哎呦，你说你怀疑他们这个关系并不单纯？
好兄弟，好兄弟，
有个队友就要保着他打，可能是大哥。
对，是大哥。
对，这个很讲义气的，但最后看起来并不是这么一回事，最后是大家一起死，大家都不要活。那 Fnatic 确实是顶不太住 LNG 现在的一个攻势的，第2次的巴龙进攻，选择是要来压一下下路高地塔的血量。
poke 阵打到这没什么力了，输太多了。主要这个 poke 阵是拿来 poke 这个阿奇尔的，就大阿奇尔太肥了。
哎呀，只能说今天选到 poke 阵的，好像就还没有一个好下场过。
没什么好下场。poke 阵主要是流行在 S 几啊 ，S4吗？那个时候吧。那时候拿 poke， 那时候大家都很喜欢打团吧，如果我没记错的话，结果人家就开始选 poke 阵，就是 counter 打团的。
这一个3件套的杰西刚一个大炮打在一个2件套带魔防鞋的他身上是没有伤害，血一滴不扣的。那反而是好像突然一波的开团，选择的目标是 Trimby 开了对方算是比较坦的一个瑞尔，还能开成半血，而且这波还能再往下拉扯。下路高地塔已经没了，但是这波是靠的一个推的2个人，而且后面他仔还关注了2个，关到的是对方的 C 位。Z 卡再跳进来，随着是 Gala 的一波输出手脚 double kill， 在高地塔下的鳄鱼也都要被给收割下来，这是一个 triple， 有没有办法完成是 Gala 的一波 penta？ 剩下来是对面的打野跟 AD 仅存活，1上了墙，但是 Gala 往前，这次准备要杀疯 ，Rizzo 在脸上按了一个金人，那这次要给 Gala 一个机会了，但没有 Scout 把人头给截走。刚好滑到了门牙塔前，收下属于他的 double kill。LNG 准备要借此一波收下比赛，在30分钟前拿下他们的第1胜。
我说实话，我知道为什么他选塔利亚，他玩的蛮好的，他打团的细节就是该中的技能都有中，可是这版本就真的很不适合野核啦。然后 Scout 真的好强啊！我刚刚会单一直在看他的细节，各种
滑来滑去，
很强，
输出打满。
他那一波，我觉得他刚玩的很好的是，他知道那个岩缺要抬他没有停下来戳人他直接快步走出去，不然他被抬到还不好说。
如果 Scout 被秒了，对方最肥的点位倒了，Gala 或许也没这么好输出了。
有这种中路难怪这么猛。
有这样子的中路，几点团练？
几点团练？1点团。卡桑蒂没毛病，双膝成型了，拿个坦克，卡桑蒂又硬又能打又硬的，卡桑蒂圣经。
杰西冒开，然后
就拍一下，
但他看起来他想做更多的事情，他觉得他不仅仅于此而已。下路要来抓阿兵了，这是一波单人线2+1，把墙壁给关掉，还要再追，但阿兵退的速度有点太快了，追不到。但开到凯撒的发育，2件套在18分半就已经掏出了那欧。这个胜利期望值也是在短短的15分钟当中已经变动了3、4次。但现在是在慢慢的往 KT 这个方向去做增加。
这样子玩的话，我是觉得我是觉得这样玩的话 ，BOG 打着打着就要输了
就是那种明明有那个优势可以靠，明明好像不用做太多的事情。
应该说他们的阵容要拿优势的，
是在
正常发育的情况下，我觉得右边强比较多。尤其是如果说这个卡桑蒂没有捞到头的话，我觉得他们这边的优势就在于他们的中野属性比较强，但这把没有玩出那个中野属性强的那个点，然后上路这个卡桑蒂右边有点处理不了，但是这几波团卡桑蒂都还没出手就输了，
就有点 BOG 整体的团战还是太急了，就沟通看起来是有点分裂的，
对，
就导致这几波的团战
炮车，
哎呀漏了，这个心态
心好痛，
在劣势的时候，这种时候最容易遭受到打击。但 BOG 的话就真的比较可惜，阿兵还是成功拉扯掉了这一波，而且是中。恭喜，就是这把比赛真的刺激，真的是带来了一场非常
他这个卡桑蒂，你们阵型一乱，这卡桑蒂就把你们全杀了，
墙壁
一个一个击破了。
是墙壁一盖，另外一边也是把鬼灵之握给交了，两边大绝的互换稍微终止了一下这一波的攻势。但 BDD 现在扛不住 poke 了，
打到这里已经没辙了。我觉得这手卡桑蒂选的太好了，右边4抢感觉应该抢卡桑蒂的，
但最后很可惜哦，这一选下来，最后我觉得唯选的厄萨斯可以来去应对一下，但没想到的是，
其实也不是说不能应对，他玩的蛮好的，但就是中间大家都有失误，就失误到后面变得这角色变无敌了。
就卡桑蒂的容错率还是太高喽。角色所带给团队，尤其阿兵的掌握度又特别的高的情况下，真的带领了团队从劣势一路翻到现在9-1开的局面。
那我觉得这个扎克应该要买那个，那个叫什么？降模仿的那件装。
你说深渊面具？
对啊，我觉得 CP 值蛮高的。
是稍微帮这个 BDD 降一点模仿，尤其 BDD 现在也是有死帽，伤害应该要起来了，但是还是落后一件装备。稍微翻到卡桑蒂，其实打的伤害还算不错，第一时间兵得往后，但他有好战的。往后给他个5秒钟，
他这手好战出的真好，
就往前，
他可以去前面一直白目。
他知道他第一时间被开到，绝对不可能死。
这个人平常一定有这种 AIN，
太强了。这个打团他是很有一手的，阿兵，这个装备上的理解。那反而是 KT， 现在真的也是没什么办法，只能看着 BLG 予取予求。紧接着3分钟有远古龙，而50秒钟则是下一条的巴龙。这场比赛已经来到43分钟了。虽然说 BLG 领着大优势，但 KT 还是很顽强的在挣扎着。
你没办法，不能放弃啊！都打到这了，怎么可能说放弃就放弃？
尤其这
2还没爆之前，都还有变数嘛。
两边并不是完美的，两边在这场比赛都是有失误的。你不难保证下一个失误会不会就是翻盘的关键。
不过说实话，就8291开啊，因为右边的上限都到这了。那个凯莎后期的上限就是不会有蔡雅高，没办法，机体就是这样。为什么大家都选蔡雅？就是因为蔡雅的后期就是一定比凯莎强。
但两边各2件 GA，BLG 双 C， 而在另外一边则是厄萨斯跟凯莎。
然后卡桑蒂的上限也开得比这厄萨斯高。杰西塔利亚我觉得算是塔利亚稍微优一点点，但是因为阵容的关系。这个塔利亚很难越过那个卡桑蒂去打到其他人，所以有点被抵消的。
一炮打到了横死1/3，但现在很明显想要开团，开到的是一个 on， 但是这边交出鬼灵之沃克，直接进不了龙坑，下了龙坑必须得闪现上墙，巴龙没抢到。那 KT
收毛加重击3000就没了，怎么抢？
已经失去了跟对方最后一搏的能力，只能再次居于守方。
玩不了。这时间点我想一下，瑞空。抬到也没用啊，跟不到啊，除非瑞空等一下杰西跟叉站一起，被瑞空 RW 接起来，然后接叉牙闪现台，只有这个画面会
接这个扎克闪现台，
不叉不那个塔利亚，
在
塔利亚闪现台，就只有这个画面会赢。
但 BLG 他们这2个双 C 都有 GA， 在 GA pop 起来的时间点，卡桑蒂绝对是有办法撑住的，
没用啊。pop 起来等死啊！
哎呀，但现在反而是有人的 GL 这边打出来，但是 King 在第一时间吃到3个人的伤害，就有点顶不太住。但往后这边一抬又抬回来3个人，这波 Q3 卡桑蒂又打出了2个人的 GL， 我的天呐！雅哥在下面先出完了汉斯之后，杀手本能杀过来，想要在力挽狂澜，但是这波 BLG 是一个人都不愿意倒下，想要把 KT 的成员一个一个全部收光。收下 Ace 的是我们的阿兵，再次出手，直接要将这把比赛给收了下来。在45分钟，
我会出手。不打那个画面真的看了好多次哦，就是那个一个 AD 在塔利亚在卡桑蒂面前晃啊晃啊晃，然后被带到塔下死了。我的已经好像不是第一次发生诶，第2次还是第3次诶。
是，但不管怎么样，我们要恭喜的是 BLG 拿下今天最后一次。
3效修护，启动年轻健康光彩，
双倍浓郁，纽西兰乳源乌瓦红茶，立顿纯奶茶欧蕾。
Make a Prum and Pyoshi coming behind you, hugging you. I know that you guys are really close. What did it mean to you to play the first game at Worlds against Pyoshik and also winning against him, taking the revenge?
오늘 사실은 경기 전에 이제 분장실에서 표식 선수와 좀 이렇게 상호작용하는 그런 모습을 볼 수 있었어요. 이렇게 메이크업 받고 계실 때 뒤에서 와서 표식 선수가 껴안고 있는 그런 훈훈한 장면을 제가 목격했는데 이렇게 또 올해 월드 첫 경기를 표식 선수를 상대하게 된 소감은 어떠신지, 특히나 1년 만에 리매치였잖아요. 어땠나요?
일단 창현 형 같은 경우에는 워낙 잘하는 선수라서 이번에 좀 많이 신경 썼고, 그리고 BLG, he says.
And aiming, getting a first blood on the Kai'Sa is gonna make KT fans extraordinarily happy.
Yep.
This is the champion he kept getting. I think it was like a 10-game win streak, and everyone was like, why? Why does he keep getting Kai'Sa able to punish the overextending Elk? Now, BLG was able to deny the actual pickup of the Herald, but they won't get the objective themselves. But with aiming picking up a kill on the bot side of the map, I think KT is still going to be very happy. A lot of CS denied here as well to Elk on trying his best to pull the wave back so that BLG...
Her piece of
Whoever has to face off against whichever team loses.
Agreed.
Because it's looking rough. Aiming, as mentioned, has been able to stay up, but at this point, like 16 to 70k gold, it doesn't make that big of a difference. His GA is still on cooldown as well. And with the gold, basically... What if?
And you can see it here.
LNG aren't necessarily the most proactive team, but they're championship. Oh, Rakan mains.
Oh, yeah,
you know, I mean, it's a champion that whenever they get their hands on it, it's just fantastic at finding it.
The engages there, good flick back, but onto Razork. Scout boops him away, and straight away his 4th kill. Now Trimby, Oscar in a bad spot as Zika might 0.3k.
Dominated the group stage, which would be considered the Swiss stage right now. Maybe
with KT winning that last game, a lot of stakes at the end of the day.
yeah. I'm looking forward to the regional overreactions.
Into KT as they come on the stage, and of course have home ground support. I mean, a historical organization. Yep.
And we'll see if he's able to maintain that level, because I think high pressure situations have been this player's kryptonite. Okay.
Bravo mesdemoiselles. Camille Thomas, nommée cette année dans la catégorie Révélation soliste instrumentale. Et Béatrice Véron au piano. Bravo et merci.
想要零广告、下载音乐并离线播放及背景播放吗？试试 YouTube Music Premium。
Thank you. forever.
I never hold back.
Bravo mesdemoiselles, Camille Thomas nommée cette année dans la catégorie Révélation soliste instrumentale et Béatrice Berru au piano. Bravo et merci.
YouTube Premium 是零广告 YouTube 外加影片下载功能，让你能在空中边看料理节目边吃飞机餐，免费试用1个月。
我觉得如果今天是我自己自学的话，我真的是完全不知道从哪里开始，而且效率一定会很差，也会知道考试的口说也是一个大重点的决心。跟你说你要是雅思2个人，然后帮你雅思算命，这样帮你加上妹跟托托器有帮助。你不一定非常多使用这个 B， 我说这样等的一个的要拍这。大家全体的来一起监督我。好的，我现在呢要来亲自测图资格的运。讲完了，还是会有错。从第2大题开始我就不行了。我不想考了我现在已经开始阅读障碍了，我看不下去了。谁考下去，谁看下去？我写不下去了啦，嗨！然后我已经进入到一种我没有办法再专心写下去的模式。我每次阅读写到后面，我都变成这样的。等一下，还饿了。没写完，阅读考完了，现在要来改，看我几分。好的，各位，我现在呢要来公布我的听力阅读的成绩，很惨惨到我不敢公开我的分数。反正就是我现在目前前测就是我的第1级的分数，我的听力是4.5分。如果我一开始就很厉害的话，那我干嘛要拍这个企划嘞？所以没错，我们接下来3个月，我们就来好好努力。OK， 各位，我现在呢来邀请妹一个晚。
先自己写这篇文章，看的切题性，它上面要说的是基本要达到7分的门槛，我现在以7分的标准来要求你。那大部分的学生都需要6.5分到7分左右，基本上6.5分到7分，大学可以随便你填的。他说要有一个 present a clear position throughout the response， 表示你从头到尾都要很清楚的立场。那在这边呢，很明显我看不出来到底是想要贴入的。所以这边它需要你能够有逻辑的 logically organizes information and ideas。这边呢，很多种方法讲话的话，雅思不会过 ，Hello， 东西好好吃哦，就是用这种方法讲话的话，雅思不会过 ，Hello。接下来呢，这边呢很重要，在 coherence 这边你需要跟你危险。要使用不同的单字，同样的单词，你这边呢，你也需要用 less common lexical items， 就是你必须要用一般人比较少用的字。这边单字量是明显不足，所以呢，我的估计是至少要120个小时的自学的时间。
120个小时是多久啊？
就你一天1个小时的话，120天嘛，你就稍微算一下。对
，OK。
所以单字的部分你需要120个小时时间，尽量去累积它。再来是文法 ，grammatical range and accuracy， 不是只有文法对，我需要你更多的句型，所以主动式可以变成被动式，可以再加上啥呀？你在看这啥？New airport， 或者是 the development of new airport。那几个这边我稍微整理一下，刚刚我讲的就是切题性的部分，离题蛮严重的，文法的错误蛮多的。我这边私信也建议你需要一个完整的文法教学。再来，逗点不能连接2个句子，现在在荧幕前面让全部粉丝看，跟我念3遍，中文逗点不能连接2个句子，自己说。
逗点不能连接2个句子。
好，动名词的概念薄弱，所以我觉得你要认真去查一下整个句构的概念。这边呢，我给你一个整体的一个建议，从错误可以看得出来，我觉得你一直以来都是吃老本，就是用国高中的一直在用自己的英文。这个短句英文是看不出来你的文法底子的，因为短句可以写对，所以你可以很巧妙的掩盖文法底子的薄弱。所以我这边真心建议你必须把文法底子先一个一个先奠基起来，这样子你才有机会从5.5分往上到6.5分到7.5分。希望今天的分析你不会太生气。
不会，因为我自己也知道我文法很弱。
OK， 好，现在在荧幕前面发誓，你10次作业都会做。
我10次作业都一定会做。
那我们下次再见，然后希望你能够把这次的作业完成。
好，拜拜。
It's personal。
那我现在就要问你一个问题。
哦哟，很突然。
我们并没有先 grade 好。
没有，刚 妹才突然说，我等一下问你几个问题。
而且我们是热的，刚刚才收到的剑桥第18册，所以目前应该没有几个人看过这本书，所以我就开始问咯。第一部分你只需要5秒钟，5秒钟的时间，你自己斟酌可以回答几句话。Number 1, let's talk about paying bills. What kinds of bills do you pay?
Well, I usually pay rent bill for my house every month.
一个活到25岁的人可能会支付的租金啊、电信费啦、电费、水电费、瓦斯费等等。
对
I pay for my rent, my phone bills, and my electricity, water, gas bills. 这个时候雅思考的不是你会讲几样东西，而是你能够讲出什么所以然。你可以说 which is a lot to me， 很多，我压力很大 ，I'm very stressed， 这样就会高分。所以当你在那边回答是用数这种流水账的，你就会低分。这些东西对我们来说，你都没有文法你都一直不断的用单字累积。我觉得我们喜欢的是一个深入的答案。所以很多时候我常会觉得这个策略可能是真的不用想太多，甚至你骗人都可以。
对，我就想太多了，我就想到那边就应该选好讲的那一个。
所以通常都是走好走的路啊，你干嘛在考试那天突然间想要对自己诚实，然后讲了超难的答案？那现在我们要讲难一点的问题咯。这一次你的答案要长达10秒钟。预备
Part 3 哦
Part 3。所以我们现在已经跳过了2分钟的演讲。我们现在只要来到 Part 3了。So you've been talking about some foods you learn to prepare. Now let's talk about young people and cooking. All right? Okay. What kinds of things can children learn to cook?
I think children can cook easier foods by themselves. For example, they can cook like desserts, such as cakes or muffins, and etc.
这时候比较好的策略不会是再讲更多甜点，对不对？所以你是现在走的策略是再讲更多的甜点，你是不是可丽露也要来一下？对，可是你现在就知道，讲更多甜点不会增加你的分数，你要开始往深度去讲。你想知道你的分数吗？我们现在来看一下雅思的评分标准。你的口说分数，从你一进去这个考场，一直到离开有差不多12到14分钟的时间。雅思考官的评分标准呢，是以这4个来判定的。好，我们来一个一个看哦。首先，第一个 fluency and coherence， 你觉得你的流利度跟这个连贯性怎么样？
不好啊，
没办法连贯，对不对？对，所以你需要一些方法。好，所以我们会希望说，学生在考试之前，你可能要需要学会延伸的方法，1+1答题法，尽量挑一样东西讲之后呢，去讲更多的内容。那像刚刚第3部分，你觉得小朋友需要煮什么？你可以说 ，Well, I think they can cook simple dishes such as sandwiches, which requires only a few steps. 只要几个步骤。All they need is 2 pieces of bread and maybe a few pieces of lettuce, a piece of cheese, a piece of ham, a few pieces of tomatoes, and you can make a sandwich. 好，这样就会变成你好有深度，你不只会讲一样东西，还可以延伸。
所以其实就算你只讲一个，就一个就好，但你就是延伸。
比较好的都是一个。如果你要考到7分，这个 fluency 跟 coherence， 第一个你要 speak at length， 你要长度够长。而且没有呢 noticeable effort or loss of coherence， 看起来没有很挣扎，并且你的句跟句之间并没有损失所谓的这个连贯性。
OK，
然后再来呢 ，may demonstrate language related hesitation， 因为英文不好，所以有点迟疑，这样就考7，因为9分更厉害。Now at times，repetition， 如果你一直重复自己讲过的话，像有些人会喜欢说 my uncle he， 好，这样就会扣分，因为我觉得整个连贯性这边很弱。然后再来呢，不要太常纠正自己。好，譬如说你说 my uncle she is a doctor， 等一下 she，
错就错了嘛？
对，错就错，你就直接错下去，因为其实你的分数不会因为一个错就得到很烂的分数。雅思考官评分是给一个整体的分数。然后再来 uses a range of connective and discourse markers。Discourse markers 就是连接词，连接词就是当你讲说 ，Well, first of all, you need something. Next, you need something， 就是你用一些连接词让别人听懂你在讲什么。 你会帮助我们了解说，哦，现在你要讲的是举例，现在你要讲的是反对你刚刚讲过的话，所以我们会听得很清楚。这个是第一部分。好，那我们现在移动到呢 lexical resource。好 ，lexical resource 就是 gave by the vocabulary。你觉得你的单字有7吗？
没有。
7分的定义是什么？所以我们来具体讲哦。A uses vocabulary resources flexibly。你要能够弹性的使用一个单字，也就是说，如果你在那边 the bell 一直讲同一个字，就会扣分。
就是要用别的字去代替，
用不同的单词，你可以讲 the mortgage，I pay the rent，不要因为我问你什么东西，那个字就一直出现。所以刚刚的单字部分，我觉得弹性比较少。然后呢 ，discuss a variety of topics。雅思7分的学生要能够讨论蛮多不同的话题。历史你也要能够说 ，Well, I don't know much about history, but I do enjoy learning about the Second World War。
反正就是只要问到你不喜欢的东西，你还是可以讲出个什么。
我觉得只要你有准备好，不喜欢也可以讲。即便是母语人士哦，你不要以为英国人啊或美国人考雅思都会考满分哦。这跟你是不是母语人士没有关系，是跟你接话的能力。
因为我发现好像雅思是它不完全在考英文能力。
雅思7分的重点咯，你要能够用到 less common 比较少见的单字，或者是 idiomatic vocabulary。再来就是所谓的
完全在考英文能力。
雅思7分的重点咯，你要能够用到 less common 比较少见的单字，或者是 idiomatic vocabulary。再来就是所谓的 idiomatic language， 通常就是整套的句型。譬如说，你会去健身房吗？
会。
经常吗
？Once a week。
Once a week。OK， 所以你可以说 on a regular basis。这样就高分了，因为规律的它就是高级英文。好，再来哦，你能够体会到什么叫 style？style 指的是啊，你不要把写作的字用在口说里面。比如说很多人会觉得，是不是越难越好，并没有啊。是。当你把那个 nevertheless 拿到嘴巴来讲，你会觉得你好怪，我为什么讲到嘴巴里面？那当然相反的，嘴巴的字，比如说 anyways 这种字，你居然用到写作里面，扣分，就觉得你好像没有文体的概念。collocation 呢，就是搭配词。很多人都会误以为是 convenient stores， 可其实不是啊，它是便利性 convenience 加 stores， 这些东西都是需要背，你不可能就是自己乱猜，自己乱猜一定是错啊。好，所以这个是你的英文单字，绝对是表现在你产出的语言上面。好，然后能够 paraphrase， 你刚刚讲过的内容能够重复讲。譬如说，当我问你说，你喜欢甜点吗？你可以说I don't have a sweet tooth， 我没有甜牙齿。来讲是吃甜食的英文。要考到7分的文法需要呢 ，a range of complex sentence structures， 复杂句就是要有 and or but so since when well because 这种句型。那刚刚他好像
没有，
要能够掌握到复杂句。那一个很好的方法是你可以用关带啊，因为我们讲话的时候我们看不到逗点啊，你管它有没有逗点，你只要讲就好啦。而且不能一直重复用同一个句型，所以不能从头到尾就复杂句，都是用到 which。然后再来呢 frequently produces every sentences， 所以即便你是简单句 frequently produces every sentences， 所以即便你是简单句，可是你从头到尾的错误都很少，还是可以高分。所以你可以都讲简单句，所以你可以用这种方式让你的英文可以加起来，觉得好像还不错。那如果说你有一些文法的错误一直持续的存在，譬如说第三人称动词都忘记加 s，它就扣1次，它不会一直扣。文法的部分你觉得你几分？你有用到复杂句吗
？4分吧，
没那么惨，我觉得你没那么糟，
因为我文法超弱的
也没有到那么惨。其实雅思如果要到5分或6分，其实就是你的错，不要影响到我们的听力，可能会5到6，但是要到7，你就要能够产出没有文法错的句型，这是你的目标。
好，
最后就是 pronunciation， 你来看一下雅思7分的标准是不是很好笑？他说呢，你有6分的特色，可是没有8分的特色，是不是很好笑？
针对我自己个人吧，对，应该要怎么样去练习？
我会觉得，因为第一个，我感觉你好像还没有进入状况，对，所以你需要先了解雅思3个步骤是有策略的。第一个策略，你应该知道什么叫1+1答题法，对不对？你有很多方式可以讲。当你被问到说 What's your favorite food？ 你为什么要讲10种？你应该讲1种，然后就讲这种，讲多一点。所以你可能要练习如何延伸，这是第一部分。然后接下来一部分单字的部分，要不要找我们？有时候我真的觉得知识就是力量 ，knowledge is power， 而知识很容易 ，a click away。你只要每个礼拜上 6 Minute English 或是 Lingo Hack 这2个 BBC 英国广播公司的节目，他们都是免费的，每个礼拜更新，可以每个礼拜就是设定时间，你一定可以快速填补你脑中需要的那些知识。发音的话呢，多跟读，好，所以看一下我的 Reel， 里面有教跟读的方法。
那我可以问我总体现在的程度大概在哪里？
如果你想要到7的话，现在有点难度。目前的话，我觉得单字、文法各方面的驾驭程度都没有到达一个很有自信的态度。我觉得到6都可能会有 good days and bad days。如果他心情好，考到6分；如果今天考官心情不好，可能考到5分。那你不会希望你的命运是放在赌这件事情。对，这是前面的观众，如果你要准备雅思，这是你的评分标准，好，官网上面可以下载的。OK， 加油喽！
Have you ever forgotten to pay a bill?
Oh my god, all the time. I think a few months ago, about 2 months ago, I almost had my electricity cut off and water cut off because I totally forgot to pay. I just moved. I don't know where to pay my bills. So when I got the notification, it was already 2 months later.
OK， 再一题， Is there anything you could do to make your bills cheaper?
I think if you pay with your credit cards, sometimes you get a discount. Some credit cards give you cash back, but it depends on the credit card companies, depends on the banks. You need to figure out yourself. 你有没有觉得我很自然？
很自然。
对不对？那自然来自什么？
来自
生活经验，
生活中就是
跟大量练习。找对老师当然很重要，这本来就是一个表演。你不要忘记雅思从头到尾就是展现给考官看，12分钟，你像孔雀开屏一样，你要给他看你发音有多好，单字有多好，文法有多好，跟你连贯性哎，你本来就是应该要准备好啊，不要裸考，同学，你宁愿裸奔也不要裸考。他已经上。应该要准备好啊！不要裸考，同学，你宁愿裸奔也不要裸考。他已经上过听说，他现在上读写课，我现在非常期待他能够有什么样的进步。So see you.
See you. 好啦，赤裸的那个雅思讲评已经结束啦。总之呢，这支影片的主要就是要跟大家报告，我要正式成为雅思考生了。总之呢，拍这一系列的影片，目的就是为了要请大家好好的督促我，因为我就是一个非常需要被逼的人。那我平常呢，也会在我的就是 IG 啊分享很多考雅思的一些生活。那如果各位呢也跟我一样，也是同时在准备雅思的考生，或者是你是我的学长姐，曾经有这个经历的，也欢迎就是在底下留言跟大家分享。那我这边呢有一些里兹蚂蚁的线上课程，还有他们实体课的折扣码连结，是专属给我的观众的折扣码，我会都放在影片下面的资讯栏。那我接下来呢就是会上里兹蚂蚁的读写课程，另外呢我觉得我应该也会上他们的那个文法线上课，因为我现在真的非常需要像托托讲的，从最基础的文法开始打起这样子。好咯，那我们就期待下一集咯，下一集大概预计
还挂着氧气具，简直猪队友！威猛先生洁厕清香冻，给你真干净，每次冲水360度零死角洁净，你的洁厕神队友庄臣。
In this video, we're going to cover Newton-Cartan theory, which is a version of Newtonian gravity that involves curved spacetime. We all know the simple Newtonian law of gravity from high school physics. During this video series, we've been working up to a relativistic theory of gravity called general relativity, which is much more complicated because it involves tensor calculus. In Newtonian gravity, we calculate the motion of objects using force vectors and Newton's second law, F equals ma. We use Galilean transformations to change between inertial frames, and we have a universal time coordinate t that all reference frames agree on. In general relativity, we have a curved spacetime, and we calculate the motion of objects using geodesics in spacetime. We use Lorentz transformations to change between local inertial frames, and we use an observer's proper time tau to measure time along curves, since the coordinate time changes for each observer. There's a pretty big gap between the simple Newtonian theory of gravity and the complicated general theory of relativity. The good news is that there's a theory that sits in between called Newton-Cartan theory that can help us close the gap. Newton-Cartan theory uses curved spacetime and geodesics to calculate the motion of objects, just like general relativity. But it uses Galilean transformations and a universal time coordinate like in Newtonian gravity. To understand this Newton-Cartan theory, we need to review the Poisson equation for Newtonian gravity. The standard law of Newtonian gravity tells us that the force of gravity between objects is equal to the gravitational constant capital G times the product of the two masses divided by the distance between the masses squared. In this case, the ER basis vector points out of the Earth's center, so the force on the lowercase m mass points in the opposite or negative direction, towards the center of the Earth. We can also rewrite this law as the force equals the lowercase m mass times the gravitational field lowercase g. The gravitational field G is a vector field surrounding a mass that tells us what the gravitational force on an object of mass 1 would be at every given point. The presence of mass causes what we call a negative divergence in the gravitational field. If we have a vector field V, then a positive divergence at a point tells us that, overall, the vectors are leaving a box that surrounds that point. A negative divergence tells us that, overall, vectors are entering this box. And a zero divergence tells us that there are an equal amount of vectors entering and leaving this box. The divergence of the gravitational field at a point is always equal to negative 4 pi g times the mass density rho at that point. This is an equivalent way of describing Newtonian gravity. Now, the gravitational field requires a vector at every point. But it turns out that we can describe a gravitational field using a scalar at every point, called the gravitational potential phi. The gravitational potential is high, far away from the Earth, and low, close to the Earth. The gravitational field is just the negative gradient of the gravitational potential. The gradient normally gives us vectors that point to the highest scalar values, but the negative gradient gives us vectors that point to the lowest scalar values instead. And this is what we want for the gravitational field, where the field vectors point to the lowest gravitational potential. So if we know the gravitational field is the negative gradient of the potential, and sub this into the formula for the divergence of the gravitational field, and then cancel the minus signs, we get Poisson's equation. This tells us that the divergence of the gradient of the potential, also called the Laplacian, is proportional to the mass density rho, where the constant of proportionality is 4 pi g. This Laplacian operator is a bit like a bump detector in the potential. Anytime there's a bump in a scalar field, the gradient of that scalar field will cause vectors to point away from the bump if the bump is like a well, or toward the bump if the bump is like a hill. Since vectors are pointing towards or away from something, this corresponds to a non-zero divergence of the vector field. So the Laplacian operator helps us find bumps in scalar fields, which are basically locations where the gradient of that scalar field has convergence or divergence. So looking at Poisson's equation again, the mass density is always a positive number or zero. It doesn't make sense to have negative mass or negative mass density. So this means that the Laplacian of the potential is always greater than or equal to 0. So this means the divergence of the vector field that comes from the gradient of phi is always a positive number if it's non-zero, meaning the vectors in the gradient of phi point outward. And the scalar field corresponding to this vector field is shaped like a well, since the gradient vectors point to the highest potential. So basically, in Newtonian gravity, mass density creates wells in the gravitational potential, which attracts other mass, since mass always wants to get to the lowest gravitational potential. We're going to use Poisson's equation later, but for now, let's see how we can create a theory of curved spacetime for Newtonian gravity. Now, I'm going to use a common standard in relativity gravity. Where tensor indices that are Greek letters refer to all four spacetime coordinates, 0 for time and 1, 2, 3 for x, y, z. But tensor indices that are Latin or English letters will only refer to space coordinates, 1, 2, 3 or x, y, z. We're going to start with Newton's second 2, 3 or x, y, z. We're going to start with Newton's second law, F equals ma. and find that it leads to a kind of geodesic equation for the case of a gravitational force. If we have a force that's a gravitational force, then it equals the mass times the gravitational field. We can cancel mass on both sides. Then we can rewrite the acceleration vector as the second derivative of a position vector with respect to time. We can also rewrite the gravitational field as the negative gradient of the gravitational potential phi. We can rewrite this vector equation in component form, where the spatial components of position are x1, x2, x3, and the components of the gradient are the derivatives with respect to x1, x2, and x3. Moving things to one side, we get that the second derivative of xi with respect to time plus the partial derivative of the potential with respect to xi equals 0. This equation kind of looks like a geodesic equation, where we have a second derivative of a coordinate plus something else equaling 0. Let's try to make this equation look more like a geodesic equation. So let's try finding a path parameter lambda and the correct connection coefficients gamma to make these two equations match. First, we choose the path parameter lambda to be the universal Newtonian time coordinate t. Next, let's see what we get when we take the sigma index to be 0. Now, in previous videos on special relativity, I've said that the x0 coordinate is just the speed of light times t. But since we're dealing with Newtonian gravity and Galilean relativity, we're going to say that the x0 coordinate is just the standard time coordinate t, without the factor of the speed of light. So the second derivative of t with respect to t is just 0. Since this term is always equal to 0 regardless of the spacetime coordinates, this implies that the connection coefficients with 0 as an upper index must always be 0. So the upper indices for the connection coefficients are only non-zero for the space components 1, 2, 3. Now the first terms match, but let's look at the second terms. The original equation has no velocity terms. No first-order time derivative terms for the spatial components. This means that the connection coefficients with spatial lower indices 1, 2, 3 must all go to 0. So we're left with only the connection coefficients that have 0, or time, in the lower indices. Now, comparing these terms, we can deduce that gamma I00 must be equal to the partial derivative of the potential by partial xi. This is because the x0 coordinate is just t, and so these two derivatives each become 1. It is just t, and so these two derivatives each become 1. And we're left with our original equation. And we're left with our original equation. So we've determined that if we start with the geodesic equation and use the universal Newtonian time coordinate t as the path parameter, and declare that the only non-zero connection coefficients are these, with the spatial index up top and time indices on the bottom, we get equations of motion under Newtonian gravity. So this is like a geodesic equation for Newtonian gravity. So we've found the connection coefficients for a theory of Newtonian gravity. So what's the curvature of space-time for these connection coefficients? We can use the connection coefficients to calculate the Riemann curvature tensor for space-time.
会藏在织物中。日本风倍清，每天喷一喷，99.9%除菌，强力消臭，难洗织物一喷清新。日本第一风倍清。
Hello everyone. In this video we're going to be solving an interesting trigonometric equation. We have tangent 1 over x equals 1 over tangent x. And one of the YouTubers, Flammy, I think made a video, something similar to this, like I think it was cosine 1 over x, or something like that. And I just decided I should make one with the tangent. So let's see how that plays out. First of all, I have 1 over tangent x on the right hand side, which is good because it's the reciprocal, so I can replace it with cotangent. And then let's leave the left hand side as is and put it on the right hand side, so switch sides. Now, cotangent and tangent are co-functions, and they are kind of like, there's a complementary relationship. In other words, if two angles add up to 90 degrees or pi over 2 radians, then the cotangent of one of them is equal to the tangent of the other. In other words, we can replace cotangent x with tangent pi over 2 minus x. You can think of it as, for example, suppose I have cotangent 10 degrees, I can replace it with tangent 80 degrees, because 10 plus 80 is 90. Make sense? I hope it does. Now, of course, we're gonna keep the right hand side as is, because our goal is to get tangent function on both sides. How do you solve a tangent equation? If you have tangent alpha equals tangent beta, then this can be solved very easily by alpha equals beta, obviously, that's clear, plus n times pi. Because the period for the tangent function is pi, so we just add multiples of pi to both sides. So let's take this and just get rid of the tangents and write this as pi over 2 minus x equals, right, 1 over x, and that's the other side, plus n pi. Okay? Great. N is an integer, by the way, you have to say, it be positive or negative. And then our goal from here is to solve for how do you solve for x? Let's put everything that contains x on the same side, everything else on the other side. So that requires that we move the negative x to the right, so it's going to be x plus 1 over x. And then we move the n pi to the left, so it looks like this. This time I didn't switch sides because I don't know. I don't even know why I didn't, but that's what it is. But I'm going to switch sides now because it doesn't look good, right? I mean, some people write from right to left, and that's probably normal, but for some people, it's not normal. Anyways, x plus 1 over x is equal to this. So what do you do with that? Our goal is to solve for x. Never lose sight, right? So we should turn this into a more familiar equation.
Bravo mesdemoiselles, Camille Thomas nommée cette année dans la catégorie révélation soliste instrumentale et Béatrice Berru au piano. Bravo et merci.
done. Job done.
That's it.
Great.
My brothers.
Job done.
That's it.
Great.
My brothers. Land prepared.
Job done. Job done. Job done. Job's done. Job's done.
No one should be the wiser.
Job's done.
I bid him. I am prepared.
Research complete.
I bid him.
Upgrade.
I am prepared.
Research complete.
Someone covered it up.
One shall be the wiser.
Job's done.
I am prepared.
Upgrade complete.
For my brothers. No one shall be wiser.
Job's done. Job's done. Job's done.
That's a given.
Job's done.
合零广告 YouTube 与 YouTube 应用程式。一个订阅，双享2个应用程式，免费试用1个月。
Enlighten me. I am prepared.
Upgrade complete.
That's it. My brothers.
Job done. done. Green complete. Green complete.
I did.
Green complete. Green complete.
I am prepared. My brothers.
费试用1个月。
Bravo mesdemoiselles, Camille Thomas nommée cette année dans la catégorie Révélation soliste instrumentale et Béatrice Berru au piano. Bravo et merci.
It's about to start. Bring victory. My blade burns with holy fire.
Happy Hallows End.
Reporting for duty. Secret agent coming through!
Good explorer comes prepared.
The battle! The battle!
Meddlesome insects!
Burn!
Secret agent coming through!
Not on my watch.
Well played. You have been.
大家好，我是林琛。今天呢，
Asia is counting on us.
Bravo, mesdemoiselles. Camille Thomas, nommée cette année dans la catégorie Révélation soliste instrumentale. Et Béatrice Berru au piano. Bravo et merci.
YouTube Music 有多种情境的播放清单，像是你在跟深蹲奋斗的时候，试试 YouTube Music Premium。
Bravo, mesdemoiselles. Camille Thomas, nommée cette année dans la catégorie Révélation soliste instrumentale. Et Béatrice Berru au piano. Bravo et merci.
YouTube Premium 是零广告 YouTube 外加 YouTube Music Premium 免费试用1个月。
YouTube Premium 结合零广告 YouTube 与 YouTube Music 应用程式，免费试用1个月。
Always on the run.
Demacia is my home, but I'll never forget my Oni.
Bravo mesdemoiselles, Camille Thomas nommée cette année dans la catégorie Révélation soliste instrumentale et Béatrice Berruy au piano. Bravo et merci.
YouTube Premium 是零广告 YouTube， 还能独家观看所有 VIP 内容，免费试用1个月。
YouTube Music Premium 让你完整掌控你的音乐聆听体验，享受零广告，下载音乐并离线播放及背景播放。试试 YouTube Music Premium， 马上免费试用1个月。
I love to muscle. It's the only good song. its destiny. I may be merciful, but Targon isn't.
This world is frayed and in need of mending.
They'll be fine.
Sharima will live on without you.
Bravo, mesdemoiselles. Camille Thomas, nommée cette année dans la catégorie Révélation soliste instrumentale. Et Béatrice Berru au piano. Bravo et merci.
YouTube Premium 是零广告 YouTube， 外加影片下载功能，让你能在空中边看料理节目边吃飞机餐。YouTube Premium 不只是零广告，立即试用1个月。
YouTube Premium 结合零广告 YouTube 与 YouTube Music 应用程式，给你不间断的影片与专属音乐的应用程式。YouTube Premium 一个订阅，双享2个应用程式，免费试用1个月。
顺畅助消化，93% 有感回购。
Hi, I'm Toby, and welcome back to The Joy of Mathematics. It's been a minute since I filmed one of these, but I'm so glad that you're joining me again today for a relaxing journey through mathematics. I'm going to run some things across the bottom of the screen that we will come to understand in this video, but mostly we will be learning how to escape from reality. Some people do this through drawing, painting, reading, or playing video games. But we are going to get a private tour of an imaginary world with the help of my imaginary friends. Before I introduce you, let me tell you a story. When I was 6 years old, I remember a kid in my class at school saying that there were secret numbers that only he knew about. He said that the teacher had told him about them after class, that they were less than 0 and called negative numbers. I was doubtful. I hadn't ever heard of such things. I thought that if it was true, then the teacher surely would have told all of us. Maybe I felt a little hurt that she had picked a favorite student, or that I was missing out on something. Perhaps that's why I still remember all these years later. Of course, I eventually found out that negative numbers were real, but I had another similar experience several years later. In high school math class, we had a relief teacher one day. I think it was the careers counsellor. He spent the start of the hour following our teacher's lesson plan, but towards the end veered far enough off course that he said, "Have you guys heard of imaginary numbers?" We hadn't. With animated strokes, he drew a large axis and labelled one real and the other imaginary. After that class, I felt pretty mind-blown. Maybe I was yet to really understand them, but that was the first I heard of these mysterious new numbers. I had again experienced my view of numbers being expanded. A long time later, I would realize that negative numbers and imaginary numbers are in fact similar in the way that they extend mathematics. They are both somewhat intangible ideas That proved to be useful. Where the negatives come from asking what 1 minus 2 might equal, the imaginary unit I comes from asking what the square root of minus 1 might be if it existed. Now, it's in the best interests of you and I to acknowledge that we live in the real world and our actions have real consequences, so we should try to be nice to each other. I will introduce you to my imaginary friends now, and whilst this isn't a popularity contest, we will want to keep track of how many imaginary friends we have. At the moment, we haven't met any, so we can write
Bravo Bravo, mesdemoiselles. Camille Thomas, nommée cette année dans la catégorie Révélation soliste instrumentale. Et Béatrice Berru, au piano. Bravo et merci.
YouTube Premium 结合零广告 YouTube 与 YouTube Music 应用程式，免费试用1个月。
mending.
Demacia is my home, but I'll never forget Ionia.
I love Demacia. It's the only place I've been. Let's see what they're made of.
It ain't luck, it's destiny.
Bravo, mesdemoiselles. Camille Thomas, nommée cette année dans la catégorie Révélation soliste instrumentale. Et Béatrice Berru, au piano. Bravo et merci.
YouTube Premium 结合零广告 YouTube 与 YouTube Music 应用程式，免费试用1个月。
I never hold back.
I miss the darkness of the void.
Stand ready! Guilty!
I am Darkin. Your gods fear me.
I never hold back.
or Newtonian gravity. So we've found the connection coefficients for a theory of Newtonian gravity. So what's the curvature of spacetime for these connection coefficients? We can use the connection coefficients to calculate the Riemann curvature tensor for spacetime. Since gamma is only non-zero when its lower indices are the time, or zero index, we can conclude that the Riemann components are only non-zero if this lower index sigma is the time, or the zero index. And since gamma is only non-zero when the upper index is a spatial index I, we can conclude that the Riemann tensor components are only non-zero if the upper index is also a spatial component I. So the formula for the non-zero Riemann tensor components looks like this. Now, in these rightmost terms, alpha and beta are summation indices, so they appear on the top and the bottom. And since they appear on the bottom, they must be the zero index if the coefficients are to be non-zero. But this requires that the matching upper indices are also zero. But as we know, this means that the coefficient values go to zero, since the upper index must be a spatial index for non-zero components. So these rightmost coefficients go to zero. And so this is the simplified formula for the non-zero Riemann tensor components. So given this formula and the connection coefficients, we can calculate the remaining four cases for the non-zero Riemann tensor components. The four cases are where mu and nu are both time indices, where mu is a spatial index and nu is a time index, where mu is time and nu is spatial, and where mu and nu are both spatial. When we set both mu and nu to zero, we just get a term subtracted from itself, so these components go to zero. For mu with a spatial j index and nu with a zero time index, the second connection coefficient goes to zero since it has a lower spatial index. And subbing in gamma I00, we get this for the Riemann components. For mu equals 0 and nu equals j, the first term goes to 0 instead, and we get the exact same components but with a negative sign in front. This makes sense because we know that if we swap the third and fourth indices of the Riemann tensor components, we get the same component but with a negative sign in front. And for mu and nu both spatial, both terms go to 0 since gamma with lower indices that are spatial goes to 0. So to summarize all the math we just did, using these connection coefficients, we've found that there are 9 non-zero Riemann tensor components that describe the curvature of Newtonian spacetime, where I and j can be any of 1, 2, 3. But since the order of the partial derivatives doesn't matter, this means there are really only 6 independent components of the Riemann tensor that are non-zero. So in the case of Newtonian spacetime, the vast majority of the Riemann tensor components are 0, and there's only a small number of non-zero components. Now, the standard spherical potential for a planet or star is negative gm/r. If you calculate all the second derivatives of this potential in Cartesian coordinates, we get this expression, which is basically r squared times an identity matrix minus 3 times a matrix of coordinate products with a factor of gm/r to the 5 in front. In 3x3 matrix form, it looks like this. To make this matrix a little easier to understand, we can pick a point above the mass on the x-axis, where x is just the radius r and y and z are both equal to 0. In this special case, the matrix has just negative 2, 1, 1 along the diagonal and a factor of gm/r cubed in front. So this 3x3 symmetric matrix tells us about the curvature of Newtonian spacetime. But how can we interpret this matrix using our intuition? Well, remember from Relativity 107c that if we have a family of geodesics with tangent vectors v and separation curves between them with tangent vectors t, we can use the second derivative of these separation vectors to determine if the curves are coming together or spreading apart. And this separation derivative is given by this Riemann tensor term. If we take the geodesics to point in the time direction with tangent vector e0 and take the separation curves to be in a spatial direction with tangent vector ej, then we get this, where this Riemann tensor term just gives us the Riemann tensor components we just calculated, which is the second derivatives of the potential. Using the matrix we just calculated for a point on the x-axis above the Earth, this tells us that the x direction has positive geodesic deviation, meaning geodesics are spreading apart in the x direction. But the y and z directions have negative geodesic deviation, meaning the geodesics are coming together in the y and z directions. If we look at what this means visually, y and z directions. If we look at what this means visually, if this ball above the Earth follows some geodesics forward in time, it will get pulled apart in the x direction, but get squished together in the y and z directions. This is exactly what we'd expect with tidal forces acting on an object in a gravitational field. So by calculating the Riemann curvature tensor for Newtonian spacetime, we found its components were described by this matrix of second derivatives of the potential, which helped us explain tidal forces in terms of geodesics. We call this 3x3 matrix of potential second derivatives the tidal tensor, since it helps us understand tidal forces. It's also worth noting that if we look at the geodesic deviation for geodesics that are traveling in space directions only, we just get 0 for the terms of the Riemann tensor components. This tells us that, for Newtonian gravity, space itself at a given moment in time is flat. We only see curvature if we look at space-time as a whole. So we figured out that these are the non-zero components of the Riemann curvature tensor. We can now use these to get the non-zero components of the Ricci curvature tensor. Remember, we get the Ricci tensor by summing over the upper and lower middle indices of the Riemann tensor. For this case, the R00 component of the Ricci tensor is the only non-zero component, and it is a sum of 4 Riemann tensor components. Based on these Riemann tensor components up here, the first component is 0, since I and j are spatial components only. And when the 0 index appears in these slots, the component just goes to 0. The other 3 components are just the second derivatives of the gravitational potential along the 1, 2, and 3 spatial directions, which are the second derivatives along the x, y, and z directions. All of this is just the Laplacian of the potential in Cartesian coordinates. The Laplacian of this potential is always positive, since in real life we can only have gravitational potential wells that pull things in, and never gravitational potential hills that push things away. So the R00 component of the Ricci tensor, which is the time-time component, is equal to the Laplacian of the gravitational potential, which, by Poisson's equation, is equal to 4 pi g times the mass density rho. So the Ricci curvature is 0 in the space directions, but it is positive in the time direction if there is a non-zero mass density. This means that geodesics in the time direction will naturally converge together in such a way that volumes will shrink if there is a non-zero mass density in the region. In other words, if we have some mass density surrounded by an imaginary volume, this volume will shrink towards the mass density over time due to the converging geodesics pointing forward in time. So this is a geometrical curved spacetime explanation for why things naturally get pulled together in the presence of mass. Basically, the mass density creates a well in the gravitational potential, which is identified by the Laplacian of the potential, and this potential well causes geodesics pointing in the time direction to converge, as described by the time-time component of the Ricci curvature tensor. So in short, this equation tells us that mass attracts other mass over time.
牙套清洁，你做对了吗？99.9% 杀菌力，小粒径，我的口腔护具清洁定。
Now, it's worth pointing out that the Ricci tensor equals 0 outside the Earth, because the mass density is essentially 0. But this does not mean spacetime is flat outside the Earth. We know the spacetime outside the Earth is still curved because the Riemann tensor is non-zero outside the Earth. The spacetime curvature outside the Earth causes the shape of objects to change through tidal forces. However, the Ricci tensor cannot detect changes in the shape of objects. The Ricci tensor can only detect changes in volume. Tidal forces don't cause any immediate change in the volume of objects. So the Ricci tensor is not able to see tidal forces. For this reason, the Ricci tensor outside the Earth is 0, even though spacetime outside the Earth is still curved. Now, there is more to say about Newton-Cartan theory, like how we can reparameterize time using an affine transformation, or how the time and space metrics are separated instead of unified like in special relativity, but I'm not going to get into those details in this video. You can check the Wikipedia article on Newton-Cartan theory or Google it for more information. So, to summarize this video, we learned how we can rewrite the force equation in Newtonian gravity in the form of a geodesic equation, where the path parameter is the Newtonian time coordinate and the connection coefficients depend on the gravitational potential. This means we can interpret Newtonian space the gravitational potential. This means we can interpret where the path parameter is the Newtonian time coordinate and the connection coefficients depend on the gravitational potential. This means we can interpret Newtonian spacetime as being curved, described by a non-zero Riemann curvature tensor. The only non-zero component of the Ricci tensor is the 0,0 or time-time coordinate, and it is equal to the Laplacian of the gravitational potential. By Poisson's equation, this is proportional to the mass density at a point. This means that mass density of the 0 or time-time coordinate, and it is equal to the Laplacian of the gravitational potential. By Poisson's equation, this is proportional to the mass density at a point. This means that mass density causes geodesics pointing in the time direction to naturally converge toward each other, which is a new way of interpreting the gravitational force in Newtonian gravity. Now, the mass density ρ is not invariant under Lorentz transformations. The value of ρ can be different in different reference frames due to length contraction. For example, if we observe length contraction, we might see the same mass inside half the volume, meaning the mass density has doubled. So the mass density is different in different reference frames according to special relativity. This means that ρ must be the component of a larger 4x4 tensor, just like how the R00 component is one component of the larger 4x4 Ricci tensor. This new 4x4 tensor that contains the mass density is called the energy-momentum tensor, and it is invariant in all frames according to special and general relativity. I'll talk about the energy-momentum tensor in the next video.
善存叶黄素，滴滴精粹，分子小1/2，好吸收高17%，善存叶黄素。
Hey guys, and welcome back to another video on the channel. In today's video we're going to be answering another student question that's been given to me. So, we've pretty much got this question here where question 21 off some test, I assume it's worth 3 marks. But you can see it's quite a bit hefty at the moment. So, the curve y equals 3 over x minus 1 intersects with the line y equals 3 on 2x at the point 2, 3, as we can see that's there. So we're assuming this is my line y equals 3 on 2. That is a very thick pen. And this one here must be y equals 3 on x minus 1. And we can tell because it's a hyperbola of its particular shape here. So we assume there'll be another part there. What else? They intersect there. The region of the curve is the region bounded by the curve y equals 3 on x minus 1. And the line and the x-axis is at x equals 4, shaded in the diagram. Okay, so that's pretty much just saying literally that region there. That's all that sentence is saying pretty much. That the region is bounded by these curves and the x bound x equals 4 pretty much. That's all that's saying pretty much. And then it asks us just to find the shaded region. Okay, so what we're going to do is literally find and split this up. We'll find the integral between 0 and x equals 2 of the line. So region 1 is the integral between 0 and 2 of 3 on 2x dx, and region 2 is going to be the integral between 2 and 4 of 3 on x minus 1 dx. So the total shaded region will be, so I'll just say the area in this case here, so areas for the shaded region will be this integral 0 to 2 on 3 on 2 x dx plus the integral 2 to 4 on 3 on x minus 1 dx. So all we got to do is integrate it. So this guy here, integrate that, add 1 to the power, divide by the new power, so you'll get 3 x squared on 4 between 0 and 2. Here you're going to get, if you integrate that, you're going to get 3 natural log of x minus 1 and between 2 and 4. Add those together. So substituting in 2, you get 3 times 2 all squared on 4 minus 0. Because if you substitute the 0 in, that term is going to go to 0, so that's why that's there. Plus, substitute in 4, so you get 3 natural log of 4 minus 1. Minus 3 natural log sub in the 2 minus 1. This side here, that can cancel with that, so we just get 3 because 2 squared is 4, and 4 divided by 4 is 1, so you get 3 here. This here is going to be 3 ln of 3. This here is going to be minus 3 ln of 1. ln of 1 is 0, so that term is gone. So our answer is going to be 3 plus 3 ln 3. There's a couple ways you can actually simplify this. If you want, you can take out a factor of 3 and 1 plus ln of 3. Or you could bring that 3 up the front, so you can have 3 plus ln to 3 to the 3, which would be then 3 plus ln 27, but it's not really specific how they want us to answer it. All they've asked for is the exact area, and both of them are pretty exact. So either one, don't really mind. They'll probably both give you the tick anyway. They're the same number. But anyway, that was a quick little video on this question here. Hopefully that makes sense. The reason why I chose the bounds the way I did is because the line is only present up until this point here, so only you need to find that area under that curve for the line, hence why that integral is set up. And the reason why I chose these bounds here for this function is because the rest of it is only bounded by the hyperbola, not the line. So it's going to be x equals 2 and x equals 4. So that's why I chose those bounds. If you have any other questions, mate, leave something in the comments. I'll try my best to answer them, okay? But anyways, I hope you enjoyed this video, and leave a like and subscribe. And if you have any other questions, yep, just flick them through to my email.
I may be merciful, but Targon isn't.
They will feel pain they've never imagined.
Your enemy's close, and me closer.
will live on without you.
I may be merciful, but Targon isn't.
The darkness.
Kaisa. Remember me.
Shurima is where all paths converge.
Void has reached this place.
I've got your back.